Okay, welcome back. We're in section 4.2C, or module 4.2C. And so this is one sample means with the t-distribution with hypothesis tests. So first thing I want to, what is that? All right, something happened, but I hope it's still working. Want to show is this. So when using a t-distribution, we use a t-score. So as if the letters, the Greek letters and things weren't confusing enough, the lowercase t is the distribution, the capital T is the score. Right? So to help us remember this, to use the t-distribution, we use a t, capital T, to represent the test statistic, and we often call this the test score. The z-score and the t-score are computed in almost the same way and are conceptually identical. Right? So they are essentially, the z-score and the t-score are analogous to each other. They complement each other in their respective tests. Right? It goes on here. The difference is that the standard error in a t-score is computed using the sample standard deviation, S, while a z-score is computed using the population standard deviation, sigma. So let's take a look at, they have a problem that they work through here. Oops, I missed it. There we are. And we have, let's look at the 2012 Cherry Blossom Run example discussed previously, but perform a hypothesis test. It will still follow the process of statistical investigation. So the question here is the typical US runner getting faster or slower over time? We consider this question in the context of the Cherry Blossom Run, comparing runners in 2016 and 2012. Technological advances in shoes, training, and diet might suggest runners would be faster in 2012. An opposing viewpoint might say that with the average body mass index on the rise, people tend to run slower. In fact, all of these components might be influencing run time. Right? So we have some data, which I will steal from the book here. As stated, when we first encountered this data, partially shown in table 4.14, which is not here, it's previous. Why is this thing binging at me? I don't know what's happening, but I might have to find that table. Well, I might not, but we have 100 runners randomly selected. So right off the bat, I appear to identify n equals 100. Right? These runners were randomly selected from the 16,924. That probably isn't important, but that is n participants in the 2012 Cherry Blossom Run, right? And that's capital N if that's our population. If we're only interested in those people that ran the Cherry Blossom Run, if we're talking about runners in general, then that's not N, right? That's just a number that doesn't matter. But we will compare the times for the sample to data from 2006. The average time for all runners who finished this run in 2006 was 93.29. So that is the first average that we had, 93 minutes and about 17 seconds. And we want to determine, using data from the 100 participants of that run in 2012, whether runners in this race are getting faster or slower versus the other possibility that that there has been no change. All right. So that is to say, we can create a test. My null hypothesis is that the mean has not changed, right? And so we have what is it, 93.29. And my alternative, right, is we think, in fact, it doesn't say faster or slower. We just want to see if it has changed. And so my alternative is that this is not 93.29. So that is my test that we're going to run. Right? So we've got some information here. I may not have to go back to the chart because it tells us the information here. Yoink. I don't know why it can't just give me my information in the same freaking size that the rest of my information is. There we go. The sample mean and sample standard deviation of the race times in 2012 were 95.61, right, which is longer. So we've already, as far as this test is concerned, we've already excluded the possibility of showing that people are faster, right? And then we have the sample standard deviation of 15.78, right? And then, of course, with our sample size of 100, right? So a histogram was shown on the left. That doesn't matter. We don't really care. The histogram just shows that they're probably approximately normal. Let me see if I can get to 87 and get that histogram. It is this. So that's the histogram that we have of this data, right? It looks normal-ish, right? So not great normal-ish, but enough to use a t test on it. Right? So we're going to perform a statistical analysis. Right? So it asks us what are the appropriate hypotheses for this context, right? That's what I just did. I jumped the gun, maybe, I don't know. But this is your H naught and your H alpha, right? And so done. And then the data come from a simple random sample from less than 5% of all participants. That's the only real reason that we wanted this other N, capital N here. 100 is less than 5% of that. So again, our population here is only really limited to this cherry blossom run. It's not runners in general. Not terribly important for the stats part of this, but as far as the inference part of this, I can't then say, well, runners across the world match this data because we limited our population to this cherry blossom run. Otherwise, this was not a simple random sample because it was just one cluster that we examined. Comes from simple random sample from less than 5% of participants. So the observations are independent, but that skew in the data, right? We've got that kind of weird shape to this thing. It says here that we can relax the normality condition for larger samples, which we've got 100. And therefore, because of this, because we have 100, it's more than 30, we are not terribly concerned about the normality shape of this data. And that's what it says there. With independence satisfied and the skew is not now a concern, we can proceed with performing a hypothesis using the t-distribution. So let's do it. There we go. The next question they pose here is they give us this again. The sample mean and sample standard deviation are the 95.61 and 15.78 minutes respectively. Recall that the sample size is 100. What is the p-value for the test, and what is your conclusion? Right. So let's figure out the standard error. So my standard error is that sigma divided by, where is it? Or not, sorry, not sigma, but s divided by the square root of n. I lost those numbers. It's, oh, that's it. There, where is it? So that is 15.78 divided by, this was out of 100 people, so divided by the square root of 100. Square root of 100 is 10, so this ends up being about 1.578, or I'll just round it to 1.58. So that's our standard error. And then we want to compute this. Let's see, is it up here? Where did it go? It's not there. This value here, they don't have it written, so I'll just write it. The t value, that capital T value, is calculated, again, it's like the same thing as a z value, so it's going to be the same kind of formula. It's going to be that x bar, the value that we got, minus the proposed mu, right? And this is, again, this mu here came from the 2000, was it 6 or 16, whatever race. But we're assuming that that is the true value because that's the value in our null hypothesis, right? It's this value here. The whole test is run assuming that nothing has changed, and therefore that mu is the average from the previous race that we're comparing this to. And then that's all divided by, where the hell is my marker? There it is. All divided by the standard error. So this becomes 95.61 minus, I lost it, and that's not helpful, 93.29 all divided by 1.58. So that is, I don't know, let me do it. (95.61) minus 93.29 divided by 1.58, around 1.47 if we round that. And again, based on your rounding, you may have gotten like 1.46 or somewhere close and close-ish, right? I'll round it here at 1.47. That's our capital T score. So then what we need is to figure out the p-value, right, from this. And it's hard to grab this. Where's my marker? Get out of my way. Okay. So again, if we go back to the T chart, right? It's hard to find what that value is. In this problem, they've used GeoGebra. Let me grab my chart here and see if I can see. No. Okay. So, yeah, let me copy, what was that on page something, D something, Z values, T. So we have a sample size of 100. That's not the part of the chart that I even want. That's not helpful. Going to go down further. And get that. So down towards the second page of your T-chart looks like this. And as you get more and more samples, right, more and more degrees of freedom, the values change much less between each one. So they don't have our degrees of freedom here are 100, or sorry, they're 99 because we have 100 people that were surveyed, but there's no difference between these two and these two. There's a 0.01 difference between 90 and 100. There's a 0.01 difference between the 90 degrees of freedom and 100 there. And then there's not a difference in that last one. So if my degrees of freedom are 99, that's a large enough number that I can use the T chart at 100, right? And my value, my T value was 1.47. And so that tells me that number is between, if I'm concentrating just on that column of my degrees of freedom of being 100, saying 99 is close enough, then the value of 1.47 is somewhere between the first and the second column, right? Which means, since we're using a two-tailed test, that value is somewhere between 20% and 10%, or 10 and 20%, right? And so it's not great to always rely on a kind of a guesstimate or an estimation like this. But what I can tell you is that this critical p-value is somewhere between 0.10 and 0.20, right? And because no matter where in that is, that p-value is greater than or equal to 0.05, or it's specifically greater than 0.05, then I know I'm going to fail to reject. No matter what the actual p-value is, it's definitely greater than 0.05, right? Now I can't find out exactly what it is on this chart, so I'm going to pull up I think we can do it in GeoGebra. Let's pull it up and take a look. And I might have to share my screen with you. Let me unshare this and share that. All right. Maybe. There we go. Okay. So I'm going to go to probability. Yeah, I don't see it here. Table. That's not helpful. I'm not 100% sure how to do this. I may have to stop this video here and figure this crap out. Let me try it under normal. Let's see if this works. I'm going to do this. Yeah, this is close. This is still doing a Z chart. I don't know on GeoGebra how to make it do a t-test instead of a z-test. I'll have to figure it out. All they say in the book is let's use technology, but it's close. I can't highlight anything, but this number down here, 0.14156, is very close to the t-score that we would have got. And again, it's because it's close because we have a high sample size, right? And so I'm going to bail out of this real quick and re-share my whiteboard. Not that. Where's my whiteboard? There it is. And so using technology, we find that the p-value, right? The p-value of this is 0.1447, whereas when we ran it as a z-test in GeoGebra, we found out that the value is very close. It was 0.14. I can't remember. I don't know where it is. Where the hell did it go? I have 8,000 windows open. Oh, there it is. We got 0.14156. Right. Again, this is not something you wouldn't be required to pull some calculation like this out of your butt on an exam. But again, like exam 2, it showed you a GeoGebra output, and you had to identify the interval based on what it put out. You're very likely to see something like, here's the output. Can you pull this number? Basically, here's the number. You need to make sure that you just understand that that 0.1447, if it were given to you, would be the critical, the p-value, right? So, but again, because this value is greater than 0.05, right, that alpha, which wasn't stated in the problem, but is the default if it's not stated in the problem, and therefore we fail to reject. Which is a strong statement. Not only did we not find that runners were faster, because we certainly didn't do that, but we also didn't find enough evidence to support that they were slower. And so we've basically said, yeah, we don't know. We don't know what's going on. I was about to ask any questions, but of course there's not. because you can't talk to me. But if you do have questions, please email them to me. And again, there's a 7-hour difference between where I'm at, but I will respond to emails. Let's look at another thing. Oh, and again, for the t-test, I'm going to go through your homework and look if you're required to use technology to figure out that p-value. I will figure out how that's supposed to be done. If I have to make a separate video just on that, I will. Or if it's easy enough to email it out, the instructions, I'll do that as well. But GeoGebra does not look like it's set up to use a t-test or to run a t-test, so we'd have to use some other avenue. All right. What about picking a sample size? We'll talk about this. Let me zoom back in here. Now, if you recall let's talk about this real quick before we jump into the t-value, picking a sample size. How big should your sample be for a z? If you're in the z world, a z hypothesis test. We talked very briefly about this. And then question 11 on your exam, which I don't have one near me, but essentially said, you don't know what's going on. But sorry, I'm going to pause you. I'm going to go get one so that I don't fumble it up. Ow, shit. All right, it said the math department chair is interested in estimating the percentage of students who take Math 1040. They would like to be 90% sure, confident that their results of the survey are within 4% of the proportion of all students who wanted to take Math 1040, right? So he wanted to be wanted to be 90% confident, right? And then he wanted the results of the survey to be within 4%. Right. So what that means is that he wants his margin of error to be less than or equal to 0.04, 4%, right? What is the margin of error? Well, in the p hat plus or minus z star times standard error, right? This is your margin of error. So what he's really saying is, I want this expression, knock it off. So we want this. We want to see that z star times my standard error to be less than or equal to 0.04. Right? What is z star? Well, because we're 90% confident, that means that z star is 1.65. And then this standard error is given to us by the square root of p times 1 minus p over n. Right? Now the trick here comes because we don't know what P is, right? In order to get all of our bases covered, we're going to use P is equal to 0.5. Because if this is the case, then the standard error is maximized. The absolute biggest error that you can have is when your probability is 0.5, which makes sense because if the probability is like 0, then 0 times who cares is 0. So if you're at 0, it's going to end up being 0. If you're at 100%, that 1 minus P is a 0, and you get 0 again. And then in the middle, you have this bump, right? And so this is the key to that problem. We didn't talk about it. That's why it was just eliminated from the exam. But the key is to have P equals 0.5, and that'll maximize N, and that'll cover all of your bases for no matter what P actually is, right? And so if I plug those values in, Z star is 1.65. Again, because it's 90% confidence. The standard error here is the square root. Let me move this. Can I move it? I don't know if I can move it part by part. So I'm going to put that there, 1.65 multiplied by the square root of P, which I'm maximizing by using 0.5. But 1 minus P is also 1 minus 0.5 is 0.5, right? Over N under that square root. And I want that to be less than or equal to 0.04. And then I solve this thing for N, right? How do I do that? I'm going to end up squaring everything. And so before I do that, I'm going to rewrite that square root because 0.5 times 0.5 is just 0.5 squared. So this just becomes 1.65 multiplied by the square root of 0.5 squared over N. Should be less than or equal to 0.04. If I square both sides, right, I square the left-hand side and I square the right-hand side, that square is going to take care of the square root, but this 1.65 gets squared as well. But now the N is out of the square root. It's free to move around if as necessary. Everything else in this equation is squared, right? But if I multiply both sides by N to get the N out of the denominator, and so I'll multiply this by N, multiply this by N, but I'm going to divide both sides by 0.04 squared. So that will do two things. The 0.04 squared gets canceled from the right. The N gets canceled from the left. And in the end, I have 1.65 squared multiplied by 0.5 squared all over 0.04 squared is less than or equal to N. So whatever that number is on the left, I'm going to round that up to the next integer, and that's my minimum N that I would use in Z-World land, right? So this is how we figure that out. This is no surprise that since I didn't talk about this, nobody got this right. However, one person did write this down and then botch the algebra, right? So kudos to you for getting the equation. Boo-hoo to you for screwing it up. But that's how it's done. These numbers, I'll just calculate them out. That turns out to be 850 point something. Where did my calculator go? 1.65 squared times 0.5 squared, and then divided by 0.04 and squared. That ended up being 400, I lied, it's 425.3. But that has to be, n has to be greater than that number, right? Which is why we're going to round it up and not down. Don't ever round it to the nearest integer. You need to round this up because n has to be greater than that number. If you round it down, n is not greater than that number. So the minimum I would take here is 426 observations. Right? So that's how it's done in Z-World land, right? So that's from the last section. Now, the question is, how do we do this in T-World land when we're doing a t-test? And this formula that we have here, right, in T-World, oops, looks like this. If I can get my pen to work. I can't move. Why can't I move? I'm stuck. Trying to just copy it, which is clearly taking more time than it should have. Screw it. Is this. Tried to save time and I wasted it. In the t-test world, we have this. So the average, right, the sample mean plus or minus the t-star based on your degrees of freedom, right, and then multiplied by your standard error. Right? The problem here is when we solve for this, right, I had an n just hanging out there in the standard error, right? And we're going to get that in our standard error as well in the t-value, but this t-star depends on n as well, right? And so I can't use a t-star here that's specific because it has to change depending on n. And so that throws kind of a big wrench in the whole process. And so rather than trying to account for that change, what we're going to do is then just use the same z star value for our margin of error as we did in the z-test, right? And so here we have, can't even remember if I posted the question yet. No, I did not. All right. Where is it? There. All right, so, and here that's just kind of reiterating what I just said. We can perform sample size calculations to help plan a study, blah, 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 blah. We can't use the t-distribution since the t-distribution depends on degrees of freedom, right? So that's this, the t-distribution depends on degrees of freedom, which depends on sample size, right? So we can still use that z star SE for the margin of error, which is oftentimes abbreviated ME, right? So in the case of a single mean, we then can use that S over root N for the standard error. So we're still talking about then choosing our Z star times the standard error. The Z star depends on whatever level of confidence you're interested in, but then that standard error is then still S over the square root of N, right? So the question then is, which is actually what I meant to copy and just wasn't looking, is this. Why does it do this crap? It's so obnoxious. So we are conducting a university study to determine the average fee increase that students are willing to pay to help fund a new football stadium. How big of a sample is needed? So that's what the question is how many people do we need to go talk to, right? To ensure the margin of error is less than $10 using a 95% confidence level, and then we assume the standard deviation of the sample is 35, right? So how do we do that? Well, we're not talking about proportions anymore, so it's not a percent. What I want is to be my margin of error, which is again this Z-star standard error. I want that to be less than or equal to $10 or just 10, right? So Z-star for a 95% confidence level is 1.96 is what we're using. Right? My standard error is the standard deviation. It's that S over root N. I don't know N, but I know that the S is $35, or I've been told to assume that. Okay. So that makes my margin of error 1.96 times 35 over root N. And I want that value to be less than $10. And then I just solve this thing for N, right? There's a couple of ways I can do this. What I'm going to do is take and divide. It's not helpful. The left and the right by 10, and I'm going to multiply the left and the right by the square root of N. The 10s cancel out on the right, the square root of N cancels out on the left, and I end up with 1.96 times 35 over 10 is less than or equal to the square root of N. And so then I just square both sides. So that's 1.96 times 35 all over 10, all squared. Whatever that value is, once again, N has to be greater than or equal to that. If it's an integer, then it's just that value. It's probably not going to be 1, and so I'll round it up. And I get 1.96 times 35 divided by 10 squared is 47. It's almost an integer. It's 47.0596. And since N has to be greater than that, then my minimum sample study should be N 48. But you can see the same calculations. You can do this 100 times, and what you're going to get is this N on one side. This was Z star. This was S. And this was the margin of error. Right? And so we can simplify our lives rather than having to do the algebra every time. We can say, and I'm going to write it the other way, N on the left, and therefore it becomes N is greater than or equal to my Z star times S over the margin of error. And I'm going to leave this for just a second because I'm going to go back to the Z score world, the hypothesis test in Z chartland, and do the same thing, except I'm not. Oh, yes, I am, because I didn't erase it. Right? I can do the same thing here. This, where's my marker? Maybe a dark blue or purple. Well, there's dark blue. All right, dark blue, blue. When I've got my n solved at the very, oh, there it is right there, right here, right? This 1.65 was my z star. That 0.5 is the probability, right? But if I don't know the, or the proportion, sorry, the proportion, but I didn't know it. And so to maximize that, I used just 0.5. So I'm just going to leave it as 0.5 because to maximize and cover all of your bases for every possible proportion, that's the one we're going to use. But then the 0.04 is the margin of error there as well. And so in Z-land, that same little trick becomes n be greater than or equal to my z star squared times 0.5 squared all over my margin of error squared. And so we have, can I select that? How do I select? How do I do anything? How do I select? There we go. Yoink. I'm going to take that and steal it. That's not helpful. Take that, and I can't move my screen. That's not helpful. Oh my gosh, pain in the butt. And it looks like I didn't square. These were all squared over here, squared, right? And so on that last one, back this train up. This is just everything squared. And this could be the same thing, z star times 0.5 all over your margin of error. You can square that at the end rather than squaring each one individually, right? So with these guys here, minimum sample size in terms of z's in the proportion world, right? In the z chart world, and likewise same thing in my t chart world. And that is it for this one. So thanks and bye.